Good morning. I'd like to wish you a very warm welcome to this, our first digital open day for the lab. Clearly we would have preferred to have welcomed you here in person, but circumstances being as they are, we've tried to be as innovative as we possibly can to bring you an interesting and exciting and informative day and to try to explain to you a little bit about the research facilities that we have here at Blockley. When we opened this facility in 2015, we actually just had Unit 1, but through a number of larger projects, we were soon pushed into Unit 2. And as things have grown, we're now into Unit 3 and we have an IMO rig at the back. I'm very, very pleased to say that this research facility has managed to keep open throughout COVID through the innovative work of our team. And through the creativity of our facilities team here, who have made sure that the facility has been COVID safe throughout, and it means that we've been able to service the fire safety community in the important work that's been done post Grenfell and in support of building regulations, the current building regulations review, which is currently ongoing. It's been a remarkably busy year for us. We've had this facility has grown year on year since 2012. Last year we completed 23 8414 tests, over 350 components of sprinklers were tested and 6,000 sprinkler heads. And we undertook 23 bespoke tests. Not only is this a research facility, but also it's an internationally accredited testing facility. It's accredited by Lloyd's Register and UCAS. And I'm delighted to say that we are currently undergoing the accreditation for 8458, which will be the UK's world's first testing facility for residential water mist. This is really important at this particular time when we're seeing suppression systems more widely recognised in building regulations throughout the UK. So, moving on to today, what can we expect? Well, as I said to you, we've tried to put together as an imaginative programme as we possibly can. We're going to try to make it as interactive as we possibly can, so you'll be encouraged to ask questions throughout, and we will try to answer the questions either throughout the sessions or at our question and answer sessions, dedicated question and answer sessions, either at the end of the morning or the end of the afternoon session. This morning's session, we're looking into building products, and particularly those conservation issues and that conflict we sometimes see between the need to conserve energy and the combustibility of buildings, products used in the building process. People will know that we've done an awful lot of work on mass timber frame, and we're going to be talking about that a little bit later on. We've got Jonathan Evans from Ash and Lacy joining us, who has been very vocal about the use of combustible materials in the building process and how they contribute to fire load, and I'm looking forward to hearing Jonathan Evans talk a little later on. This afternoon session will start at 2 o'clock, where we'll be looking at suppression. As I said, suppression is getting increasing recognition within the building regulations now, not before time of course as far as FBA is concerned, but we've also be looking at the importance not just of the suppression system design and installation, but also we're going to try to stress to you the importance of regular maintenance as well. We've got two of our principal consultants who will be talking to you about specific case studies and experimental work that they've done to support the sprinkler rules and other suppression projects that we've been involved with. We will also look at a couple of live burns in action. Many of you will remember the large car park fire that took place in Liverpool back in 2018. Some of you will have seen the One show and the work that was done recreating that fire. Actually, that fire was recreated in our laboratory, and we've got some broader footage there which will give you some little bit more insight into the capabilities that we have at the lab, but also into the circumstances of that fire and how it spread. Finally, we'll finish the day with a broad discussion on standards. Standards are a very, very important part of what we do here now. Standard testing takes up something like 70 to 80% of the work that we do now at Blockley, both on sprinklers and on building products, particularly the 8414 testing rigs. We have 3 rigs down at Blockley at Morton at the moment, and we're looking to bring another one on stream before Christmas. So exciting times. We think we've got an exciting programme for you. I hope that you get as much out of it as I think you will. Certainly today should be informative. Today should ask, if you've got questions, as I said, please let us know. We've got a great team here at Blockley that are ready to help you. If they will either be able to answer your questions directly today as part of this online forum, or if you've got any further questions, please don't hesitate to get in touch with the team at Blockley. They'll be delighted to help. Thank you.
Good morning, my name's Gary Martin. I'm the Commercial Sales Manager for the FPA. I'm going to be your guide for this virtual lab day. First up we have John Briggs, who's our Commercial Director, who will be showing you around our test facility in Blockley.
Hello, welcome to the FPA Fire Testing Laboratory and Research Facility here at Blockley. My name's John Briggs and I'm the Commercial Director and responsible for the laboratory. If you follow me, I'll show you around the establishment. This is our sprinkler valve room, which Ian will show you in more detail later on, but it has 14 valve sets. Okay, this is the sprinkler pump room, where we have 3 pumps, a small jockey pump, an electric pump and a big diesel pump. But again, Ian will explain this to you in more detail. It's one of our best training facilities. This is our smoke scrubber, just outside the Unit 1, which is the main burn hall. The purpose of the smoke scrubber is it takes all the smoke from the fires that we make in the burn hall and cleans it. And so we discharge it as clean air, having been through several processes of filtration. But that's the reason we're allowed to do the burns and the tests that we do up here at Blockley. We're now in front of our IMO rig, which is the International Maritime Organization rig, which we first built to test ships' compartments, but we now use it for all our hot tests. So when we've got a burn, which is a hot burn, like burning parts of cars and so on and so forth, then we do it in here, because this is a completely metal shed, a metal container, so it's less susceptible to damage from heat. We're now in the Watermist rig, and we are going to be one of the first companies to be accredited with BS 8458, testing of domestic and residential water mist systems. And this is the rig in which we do that. Here we are in our main burn hall, Unit 1, and you can see that we've just got one test rigged to burn there, which is a bespoke test which we're doing. And above that you can see the variable height ceiling. We have the ability to move that ceiling up and down to about 10 metres, so that we can change what we put underneath it, and it has sprinkler heads already in it, so it's very easy to make and change the rigs as we do different burns. We're now at another part of the burn hall in Unit 1, and we've just completed this afternoon a test, another bespoke test on this piece of equipment, which we're just clearing up from now. And over here we're testing plastic waste bins to see how flammable they are, and that test is almost ready to go. And this is our sprinkler head testing laboratory, where we test the sprinkler heads, which we've been doing now for a number of years, and the demand for them is increasing, so we're doing more and more of this sort of work. So we test the sprinkler heads, and Ian will go through the detail of that later on. So that's the whistle-stop tour of the laboratory. Now let's show you what we can do.
Next up is George Edwards, Head of SPG Trials. He's going to show you a foam burning test.
Okay, so environmentally friendly foams are becoming more common, as a lot of the non-environmentally friendly foams are banned, such as anything with a chain longer than C8 is banned, and anything with a chain longer than C6 is heavily restricted in Europe. But there are concerns that the more environmentally friendly foams aren't as effective at putting out fires. So we did a series of tests for our client to see which of these foams had a better performance, and how the environmentally friendly rating sort of affected the performance of them. So we set up a variety of challenges. We did a heptane liquid pool fire. We did some plastic bottles with white spirit in on racking. And we also did some tests with plastic pallets, polypropylene pallets, stacked up. And we tested a variety of foams against them, and we also used a pure water sprinkler system as a baseline. Okay, so this is the heptane pool fire test. So that's sort of simulating a fuel spill that's caught fire. It's quite a large fire that we're simulating, so it's a 2 metre squared tray, so it's over a megawatt. And you'll see the sprinkler systems going off here. So we're testing 3 different kinds of foam, and we've got water as a baseline. So in the top right, we've got C8, which is the least environmentally friendly foam, and you can see how it's actually knocking the fire back faster than the others as the foam's sort of building up and spreading across the surface. We've got C6 in the top left, which is not banned like C8, but heavily restricted across Europe. We've got F3 in the bottom left, which is a fluorine-free foam, and you can see that after 1 minute and 50 seconds, the C8 foam has extinguished the fire. And there's sort of 2 sort of main things for assessing these systems. One's their ability to put out the fire, and the other is to keep them extinguished and make sure that foam layer that's built up has stayed across the surface. And you can see that the C8 fire is staying out at the moment. And we can see how the C6 and the fluorine-free foam have both knocked the fire back compared to the baseline of the water, which hasn't really noticed that it is being suppressed. And that's because water's not very good at putting out liquid fires, whereas the foam systems build up a layer of foam that will slowly break down from the flames. It has to build it up faster than it's sort of burning away. And we see the C6 has just extinguished just after 4 minutes, and the fluorine-free foam is still going. The flames are sort of just licking around the corners and the edge of the tray as it sort of struggles to build up a foam layer in the corners. But it should go up pretty shortly. There we go, just after 5 minutes, almost 5 minutes and 30 seconds after ignition, the fluorine-free foam extinguishes the fire. The water system doesn't actually extinguish the fire at all, so we had to manually extinguish it with a fire blanket. Okay, so we've just seen the heptane pool fire test, and next up we're going to see the pallet fire test. So we have a stack of polypropylene pallets, which you can see being ignited now. And again, we're putting them out with the suppression system, or trying to, and seeing the difference in performance. So we've got the C8 foam in the bottom right this time, C6 in the bottom left, the fluorine-free foam in the top right, and the baseline water suppression system in the top left. You can see how these plastic pellets produce quite a massive fire load, much bigger than you would get from a wooden source. And the other thing that happens with plastic is once it starts to burn, it starts to melt, and it turns from a solid fire into a liquid pool fire, which is why it's recommended to use foam systems on them. So we see with this test that the suppression system is going off and sort of struggling to knock them back to start with. And as the test goes on, we'll see how the fires get knocked down, and then once it's sort of dealt with a solid fire, it then has to deal with the liquid fire around it as well. So you can see here how the water system has actually knocked back the fire quite well, but it hasn't extinguished it yet. And same with the C8 system, has knocked it down. There's quite a bit of variance with solid fuel fire tests, which is why we're sort of seeing different results at this early stage, most likely. But you can see how the C8 fire has almost gone out, while the water system, despite being knocked back very quickly, is still burning. And you can see how the F3 and C6 system have also pretty much knocked the fire out, just dealing with the small flames. So the C8 fire is completely out now. And see how the fluorine-free foam looks like it's gone out, but there's still a few flicks every now and then. And it looks like the C6 is performing similarly at the moment. The water system, which was sort of the fastest one to knock the fire back, is still burning as it struggles to deal with the liquid fire left over. And you can see the C6 fire appears to have gone out now. So both the C8 and C6 foams have extinguished the fires. and you can see in C8 someone's just going in to check on the test. So at this point the baseline test is extinguished manually, and the same for the fluorine-free foams. After 9 minutes it was decided that it didn't look like they were going to put the fires out in a reasonable amount of time. So although they suppressed the fire, they didn't extinguish the fire. So this was a successful test from a trial point of view, as we were able to show a clear difference between the different types of foam and a difference in performance between them, which hopefully can be used to update the guidance and sprinkler rules.
Next we've got Dr. Jonathan Evans, CEO of Ash and Lacy, and he will be talking about 8414 testing and everything that's involved within that standard.
Hello and welcome to the FPA Virtual Lab Day. My name is Jonathan Evans and I'm going to talk today briefly about the 8414 test that can be done here at the FPA from a manufacturer's perspective, a manufacturer of rain screen systems, and look at the issues that we have with the 8414 and whether it has a role to play in a world where we have a combustible ban for the majority of tall buildings at the moment, and will possibly be reducing to 11 meters in height as well. Before I start my brief talk, however, I'd just like to play a short video to show how important the work is that we do and how important it is to get fire engineering right, and even when you don't actually have a fire, how much it can actually impact residents' lives.
I'm 30, we were thinking about starting a family. That's not going to happen because it would be the most ridiculous thing to bring a child into the world. And it's just, we're just trapped, essentially. And it's hard to talk about because obviously I run Leeds cladding scandal. I hear everyone's problems, and I hear so many people's problems, and it's not until you stop that you realise how much stress people are going through, and everyone's different story. And like, there's pensioners in my building that can't move, like they paid off their mortgage, like their flat's worth $0, they can't move, they have to stay here. There's people that have newborn babies that can't, we're literally just trapped.
I feel that manufacturers have an important role to contribute to what the 8414 test can actually produce. We're one of a few groups of individuals, organisations that can be asked to provide an 8414 test. We often get asked for it by designers, architects, specifiers and so on. Therefore, we're often paying for the test itself, which is a very expensive and big commitment for a lot of companies. So I think we've got a right to actually have an input on what actually comes out of the test. More important than anything else is that we need to be able to answer the questions that we get asked day in, day out by project specifiers, engineers, architects, and so on. And this is where I think the 8414 test should have a role in the future, or a derivative of the test, but currently doesn't really give us all the answers that we need. The 8414 test has been widely criticised. I'm probably more of a supporter than many people of the test, and I certainly think it's got the potential to be a very useful tool. One of the biggest criticisms that we see all the time is that it's not representative of a true facade. So it doesn't have any windows, penetrations, attachments, and so on. And people often think this doesn't give a true representation of how a fire is going to impact a real building. I'm going to come back to that and give you my thoughts. More of a concern from my point of view as a tool for designing systems and looking at safety overall is that this does test a perfectly built system in laboratory conditions. And that doesn't really reflect how I see cladding systems installed and assembled day in, day out on mass climbers in bad weather by people who often can barely speak English and are poorly trained. So it doesn't reflect the robustness of the system and its dependency on being built perfectly. And the time you're allowed to build these tests, again, is not representative, and the care that you're able to give. The classification criteria as well is just a reflection of the old 18-meter rule. So in some respects, the BR135 has lost its relevance. And I feel it's too blunt a tool for engineers to make meaningful decisions about comparing different facades that have been tested. It's also extremely expensive. Now that's mainly an issue that deters people from doing the test. And obviously the more information that people and designers can get from systems, the better. It also doesn't prove that the whole system works. It can lead to false conclusions about individual details of the system. And again, I'll come back to this. And it only really tests fire spread. There's no opportunity to measure or quantify the amount of toxic smoke that is produced by the system during the test. And that provides a little bit of a loophole to some extent, that we don't really want a test where we're replacing one problem with another, that manufacturers of materials can fill their products with limitless amounts of chemical flame retardants to suppress the fire spread, and we end up creating a bigger problem where we're creating vast amount of thick black smoke, which is possibly more dangerous than the fire spread itself. It also has a big limitation as well. There's no indication that when you test the system on day one, that in 10 years' time, it's still going to be able to pass that test. And this highlights one of the concerns, for instance, on things like intumescent cavity barriers. And again, coming back to my second point about how sensitive is the performance of the test and fire safety to those individual components and how they perform. The 8414, though, in my view, is not alone in being criticized. So what we basically have in the industry at the moment is a widespread failure. In my view, unlike Hackett, I don't think we have a chronic safety problem in construction. We don't have buildings collapsing left, right and center with structural engine failures and bridges like in Genoa. Balconies don't fall off buildings. Glazing falling out of buildings is relatively rare. People don't electrocute themselves, drown themselves in basements and so on. So it really is just about fire. So we've got to really focus on why that has gone wrong. The limitations of Class O as a method of quantifying the dangers of composite materials are being well discussed now in the public inquiry. But there are similar issues with 13501 that I feel aren't being addressed as well. So I think the equivalent weakness with 13501, for instance, is its ability to communicate the dangers of sheet polymer thermoplastic cladding, which tends to sail through it tends to just melt, burn off and get through the classification process. There are also issues, I believe, with time temperature curve testing, fire resistance testing, where combustible materials contribute to the amount of energy that's put into the furnace, resulting in the energy that's supplied externally being reduced. And I think that gives a false advantage to combustible fire doors, for instance, compared to, say, a metal fire door. And there's some areas where we just simply don't even have any tests that we can make meaningful comparisons with. Cavity barriers is one, and a very important one at the moment, but also increasingly I'm concerned about modern methods of construction, modular systems and so on. So at the moment we're talking about a two-dimensional cavity fire spread test regime, but we haven't even got to the point where we can meaningfully talk about three-dimensional systems and party wall cavities. One might ask, well, why do we still need a test at all if we're going to have a combustible ban? But I think there is a role, because British standards aren't all just about compliance. And I have this argument quite a lot when we're talking about the BS 8414 review, the British standards, and now the BR 135. A lot of resistance comes from people who say, well, there's no point in having anything in the test which is not regulated. But it's not all about regulation. British standards provide a standardized method of comparison of different materials and products from suppliers around the world. And that's an extremely useful platform to have. We also might find that low-rise multi-occupancy buildings, which come under the 18-metre or 11-metre rule as it might be, we also need to show that we can adequately resist the spread of fire there. And it's important that designers have access to tests that can show that their systems can perform well in these applications. And also, not all combustible systems are the same by any means. And again, I'll come back to that in a minute. Just going to show a couple of test results. This was the fire retardant ACM that was tested in the summer of 2017 after the Grenfell fire with non-combustible insulation. So this was a test that passed, as was this one. And this is the high pressure laminate test, a subject very close to my heart. This is Class B high pressure laminate. So it's a highly combustible material with a chemical flame retardant added to suppress external fire spread. So although this system has passed, all of the material that you can see consumed on this display has been converted basically into thick black smoke, hence the point I made earlier on. Now you compare that to this, and I apologize for the poor image. This was a test that we were involved in. It's an Ash and Lacy brick slip system. And you can see there's very little damage here. So we've spent 2 or 3 weeks and 60,000 pounds building a test rig, and only the bottom half a dozen bricks and half a meter or so really got damaged in the test. And the BR135 classification criteria at the moment really doesn't articulate the difference between these two systems that both passed, whereas this system obviously won't have produced or added any large amounts of smoke and toxic gases to the fire that broke out from the flat below, but also there's much less damage and so on. And that's not reflected in the classification criteria. This test also shows potentially the inadequacies of, or the dangers of asking the 8414 test to be a full facade test. So if you had added a window to this test and an engineer had asked you to prove that your window interface details were going to perform well, this is the situation you might have ended up in, where the actual fire and damage doesn't actually get anywhere near the interface details that you're looking to prove. So this might give the misleading impression that the details that you have around the window will perform well, whereas in fact, you've not actually exposed them to any meaningful fire, heat flux, and really tested that part of the system. So what does the industry really need? Well, we've been looking at this for some time now, and many people, as you are aware, have been pushing for smoke and toxicity regulation, because ultimately that's what generally kills people. I'm looking as a manufacturer for a test that can support a graded classification standard that allows engineers to differentiate between different systems, and that also can give us a proof of smoke compartmentation, because this, even though it's not regulated specifically, is a question that we get asked more and more. Debris and damage is also important as well. So the robustness and resilience of the building, again, this is a test which has the potential to communicate an awful lot of useful information on that part. So what I envisage is a classification criteria that can give the designers a graded appreciation of the important factors that we're looking at. And I've repeated here, if you like, the same format of the frankly rather annoying layout that we get from 13501, grading fire spread, smoke production, debris and damage. So as I've said, should the 8414 be a full facade test? Well, I firmly believe it shouldn't, because there are far too many variables in this test to actually produce meaningful information about any one particular part of it. And I think that can lead to misleading conclusions about individual elements of a full facade. Now, a full facade test can confirm that what a designer has put together will actually behave as expected. And I think we need more research to show that full facade testing might be necessary in certain situations. For instance, if the architect brings the windows very close together and so on, do we need to prove in those situations that the facade's going to behave as expected? One of the criticisms about the cost of testing is, can it be made cheaper and simpler? So a lot of people have observed the fact that a lot of thermocouple readings and so on are largely of no use for the BR135 criteria and are expensive to assemble and install. Now, when the government was actually paying for its testing and was asked to do the non-ACM test program with the BRE, it's interesting to note that they actually came up with a much simpler test, which they claim actually subjected the cladding to the same heat flux as the BS8414 test. Now, this test is much smaller. It's only 3 meters in height, doesn't have a wing wall, which again, I think is largely superfluous. And the backing structure is largely irrelevant as well. And this was designed just to test the external fire spread of the cladding material itself and the way it was mounted with a cavity. So in some respects, this is sort of halfway between an 8414 test and the tests that go into 13501 test, but at much higher powers and intensities. So yes, it can be made much simpler from this point of view, only looking at parts of the facades which are independent in their nature. But the problem is, of course, that we're also asking to add the instrumentation and observational resources to be able to feed back on added features such as smoke and toxicity. So what really is the way forward? Well, I believe we need a suite of tests that provide the answers that we need. We can't just do it with one single test. It's too blunt a tool, the scale is too large, and individual elements risk not being subjected to the fire. We need realistic tests of individual elements They also look at the key concerns at the moment. So the government are very much pushing timber construction at the moment, modern methods of construction, modular construction, where we just simply don't have the test infrastructure to make meaningful decisions on whether these are actually safe. So I think that we're being reckless in that sense. And that really worries me as a manufacturer, because I make cladding systems that can often end up on timber frame modular buildings, for instance. And if that building goes up in flames, then I'm going to be the one standing up in the public inquiry that follows it and so on. And I really don't want to be doing that. I don't want to be forced to be associated with materials that I'm not in control of. And we also need new standards to support these tests, particularly cavity barriers, which is one area, again, where we've learned an awful lot over the last 2 or 3 years since Grenfell, but also we don't have standard tests for penetrations and window interface details. And again, this all needs to be looked at collectively. And we need to add in the regulation. I know that MHCLG are looking at this for smoke and toxicity, but also debris and damage. I've seen pictures of some facade systems where several kilograms of tiles and stone have been dropping off the facade left, right and center, possibly in real life they'd be falling on people trying to escape or firefighters trying to enter the building. And again, I think there needs to be something that can convey that that's how that system is going to behave in that situation, so that maybe architects and designers can avoid putting those systems above key evacuation routes and so on. And a classification standard that really can allow manufacturers to differentiate their systems and benefit from all the hard work, research and development that they've put into their systems to create robust, resilient products that are a genuine step forward for the industry. And furthermore, we need to continue to research. There are still big gaps in our knowledge and uncertainties when it comes to design, and the behavior of fire in cavities is still not well understood. I think there are situations, for instance, where cavity barriers may not be needed. I think that the thermal integrity ratings of cavity barriers may not be particularly suitable in certain situations. So there's an awful lot of work to be done there before we can confidently say that we have a suite of tests and a set of classification standards that can allow designers to confidently design safe buildings in the future.
Thank you, Jonathan. Now we have Tim Kansas, Head of Standards Testing, who will be showing you around our 8414 facility.
This is the FPA's BS8414 testing rig. We currently have 3 of these rigs in operation. We are currently in the process of sorting out building a 4th rig as well, to allow our customers a shorter lead time, because these get booked up very quickly by people. It's a very popular test at the moment. We currently have the accreditation to do these tests for the 2015 BS8414 test standard, and then we also have the 2020 BS8414 test standard accreditation, which has a few changes in it. It's mainly around having a slightly taller test rig. And so for this purpose, this rig that you can see behind me is being knocked down and replaced with 2 slightly taller rigs, which you'll see later. We can go around to the other ones. The test essentially itself, what happens, as a client, you book out one of our test rigs for however many weeks you'll require it, and then you essentially get given a metal frame onto which you have to install your cladding system. So we do a variety of cladding build-ups here. We have tested build-ups for either for manufacturers who want to test a new build-up of a completely new system. We have tested systems that are on new build buildings, and then we've also tested quite a lot of systems that are on existing buildings. The tests that we do for existing buildings tend to be the most popular at the moment. That's all of our current clients that are on site are testing build-ups for buildings that are actually out there at the moment and occupied by people. The test itself is a fairly simple test. We have this wall, which is roughly 10 metres tall. At the bottom of it, in this sort of bush shelter shape here, we put a big fire. We have a large wooden crib, which is 1 metre deep, 1 metre tall, 1.5 metres wide. We light that crib, and it burns for a total of 30 minutes, at which point we extinguish it. At the end of that 30 minutes, you then have a period where we observe the wall to see if there's any residual burning in the system, or any fire spread that's still going on. This is a system that was tested earlier today. As you can see, the effect of the fire is really just a bit of heat scorching on the front of it. There hasn't been a huge amount of structural damage to the system, but it's a brickwork system, so it's sort of what you would expect from that. In terms of the data during the test, we have sets of thermocouples, so 2 meters above the burn, 2.5 meters above the burn chamber, we have the first set of thermocouples, that's level 1 of thermocouples, and then 2.5 meters above those, we have the second level. So the test itself starts when the thermocouples at the first level reach 200 degrees. That means that the fire has grown to the point where the test is now starting. And the flame tips will just lick up to that height. You'll see the thermocouples are sort of pretty much where the tip of that scorch mark is. And then from then onwards, we're measuring for fire spread from that point up towards the second level of thermocouples. The big difference for the 2020 test standard is that we now have a third layer of thermocouples as well, which sits another 2.5 meters taller. So obviously our test rigs have had to get slightly bigger to accommodate this, which is why we'll be moving over to our new test rigs very soon with the bigger height, and this rig's being dismantled. At the end of the test day, you will then get so if you're on site here for the test, you will get to watch the videos as they are recorded on the day. You get to see the test itself. You also get access to the data from the video from the test. Then once we have the data, we then take it off the data logger. We create some nice looking graphs in a spreadsheet for you, which explains exactly what was happening temperature wise during the test. And then at the end of that, after about 6 weeks time, we'll have compiled a report which has all the data in it. You get the BS8414 test report, which essentially describes the build-up as it was tested. It has photos of the installation in it. It has photos from the test. It has photos of the dismantling afterwards. And then you also get the BR135 classification, which essentially states whether or not it met the requirements of BR135, which are the requirements themselves are flame spread criteria. So that is whether the flames spread to the top of the test rig, and then also mechanical performance. So that's looking at large pieces of debris falling from the building, anything that might endanger people escaping the building or might endanger the fire and rescue service, potentially putting out the fire themselves. So this is an example of the cladding system that we tested earlier today. So the components that make up the system itself, we have working from the inside out. You've got the internal dry lining, which is what you normally see on the inside of the building. You then have this, which is called the SFS, the structural frame system. This is a steelwork system, sort of like a modular stud wall system made out of steel, which they fit together sort of like Meccano bits, and that's what infills inside the structural steelwork that actually makes up the floor slabs of the building. You then have on the outside of that, you will have a layer of insulation. On this specific system, it's quite a small level of layer of insulation, but obviously all systems are different. You can have up to 180, 200 mil thick insulation, depending on the individual building. Then behind that, you have, because this is a brickwork system, you have the metalwork brick supports. If it's an aluminium rain screen system, or potentially an HPL system, then you'll have some sort of vertical and horizontal steelwork helping hand system, which will then hold the facade on through the insulation. Whereas this system, you can see they have these metal support channels which run vertically, and then that ties into the brickwork at the front. And then, as you can see on this system, we've got a brickwork facade, but like I said before, we've tested all sorts of materials. You can get some systems that are just a single sheet of aluminium. We've had aluminium honeycomb systems. We've had steel facade systems. We've also had HPL, which is high pressure laminate systems tested. So it sort of depends on whatever system is on a building out there on high-rise stuff, whether it's brickwork or whether it's modern aluminium rain screen. We can test it here, and it all gets put through the same test. So this is what you'll get when you arrive at the FPA as a prospective client for a BS8414 test. So essentially you have a big steel frame, which is essentially the blank canvas that every single 8414 test starts with. Onto that, the first thing that gets added is the METSEC frame that we spoke about in the other rigs, and then you will then attach a sheathing board onto that, and then any bracketry, and then finally the insulation and the facade onto that. The way that all of our test processes start, so obviously every project starts with the initial inquiry. After the inquiry, we essentially will decide whether your system is appropriate for this test, or if there's a different test that you should be doing for your individual system. Generally, with most high-rise cladding systems, the BS8414 test is the most appropriate that we have in this country. We will then review whatever materials you're planning on testing as part of the test. We can give you some advice for if it's a system that we don't think is appropriate for this test. If we don't think it's going to pass for any reason, you sort of save yourself a bit of money by not even bothering testing it, just getting it replaced, which has happened in the past. But generally, what we'll do is we ask for the drawings of the system that you want to test, the materials involved. We'll then give you the dimensions of the test rig, so you can then create a bespoke drawing of the test rig as it sits, and what you actually want to test. And then from then we'll work out the timescales of the project, and all projects are different. So if you're, for instance, installing a brickwork system that has a curing time, or a render system, which will be the same, then we have to factor in however long it takes to cure, and that's generally based on the manufacturer's recommendations and guidance. Obviously, aluminium rain screen systems don't require that, so we can get them done not generally a fair bit quicker. And our timescales tend to depend on what the customer wants from your test. If you want the system built quickly and you can facilitate it being built quickly, then we're on hand to test it quickly. A lot of them tend to be a case of, can we get it tested yesterday, which we try our best with, and that's why we are building a fourth test rig to sort of open up a bit more and give us a load more testing slots, because at the moment our slots get booked up very quickly. However, once you're on the waiting list for a testing slot, then if we ever get any cancellations or anything along those lines, then we can sometimes shift things around and push people up the order a little bit if needs be. But the actual test itself, generally, in terms of the time spent assembling the wall, we generally say it takes between 2 and 3 weeks to actually build a cladding system for the test, and then any curing time that is required will be added on to the end of that, and then we will test it the final week, and it can only be demolished in 2 or 3 days after the test has happened. So we're generally talking from a minimum of around 3 weeks for a test to a maximum of really around 7 to 8 weeks for most systems. So hopefully that's given you a good overview of our BS8414 cladding testing capabilities. If you have any questions about cladding testing in general or facades, if you think you know of a cladding system that might need testing, or you're just unsure about what sort of systems need testing or what sort of systems can be tested, then feel free to get in touch. Our contact details can be found on the website, and also they should be sent out to you just after the event.
Thanks, Tim. We're now going to show you a case study. This is a case study on a bespoke trials/test that was done on behalf of Ibstock Brick. Your guide for this one is George Edwards again, Head of SPG Trials.
So at the FPA's fire test laboratory, we carry out bespoke fire tests for customers to help them answer any questions they might have, designing unique tests for them where there isn't an appropriate test standard. And we always aim to provide impartial advice. The test we're about to show you is for Ibstock Brick Limited, a manufacturer of brick and concrete products. They initially came to us for exactly that reason. They wanted to test a load of their products in scenarios where there wasn't an appropriate test standard, and they wanted us to design a fire and test around it with appropriate loading conditions and things like that to test them in real life situations. So Ibstock Brick wanted to test out a new adhesive material for attaching brick slips to a metal lintel. We worked with BBA and Ibstock. BBA is the British Board of Agreement, to design an appropriate test for them because there wasn't an appropriate test standard. It was proposed that a fire replicating a room in flashover, venting through a window should be used, and after a few discussions back and forth, it was decided that a gas-controlled fire, maintaining the temperature at the underside of the lintel above 600 degrees for 2 hours would be used. We controlled the gas flow using our mass flow controller, which allowed us to keep the temperature between 600 and 700 degrees. It was decided that the lintel should be under representative load, and a force of 21.5 kilonewtons was applied, so just over 2 tonne. The weight was spread out evenly across the lintel, and we used multiple weights so that the load would remain evenly distributed even if the lintel started sagging, because if it sagged in the middle and there was a robust load above it, it would only apply it at sort of 2 points. And yeah, the main purpose of the test was to see how long the adhesive could keep the brick slips on the lintel. Although this test wasn't conducted to a standard, we did base it off of several standards. For example, we based the sort of general construction and burn chamber design off of the 8414 test standard, and we based the fire load off of one of the furnace standards, and we also based the loading conditions off of one of the test standards. And through all of that process, we worked with BBA to make sure it was appropriate, and both of us agreed with what we were doing. We measured several things throughout the test. We had thermocouples placed throughout the lintel and above and below the lintel. We had a thermal imaging camera to record hotspots throughout the lintel, but most of the analysis was done on the visual observations and post-test analysis for this test. All of that, along with the test setup and methodology, went into a report which was sent off to Ibstock and BBA and approved by BBA. And we've done several tests with Ibstock now. For example, previously we tested a brick slip system on a wall, and again they wanted to test a different adhesive for that one, and we tested that against a representative weedy bin fire. Similar to this one, instead of using an actual weedy bin, we used a gas burner controlled by a mass flow controller, and I think Ibstock found us very easy to work with and easy to sort of sit down, design a test and help them answer the exact question they had, which is why they've come back to us for several tests since then.
Our last speaker of the morning is Dr. Jim Glocklin, Technical Director at the FPA. Jim's going to talk to you about the risk of timber in high-rise buildings.
Good morning, I'm Jim Glocklin, FPA's Technical Director. In this short presentation, I aim to highlight some of the property risk challenges associated with building ever taller in structural timber systems. If you have any questions you would like to ask, please submit them and we shall try to address them during the panel sessions. Many countries around the world are looking to increase the use of wood as a principal structural building material, and for some very good reasons. It has been identified that there can be significant cost savings due to its suitability to support off-site preparation and the ease with which it can be modified and adjusted on-site. As a carbon capturing material, its credentials for supporting the sustainability agenda are obvious. However, for the insurer, it presents great challenges when used for the construction of large complex buildings. It's combustible, obviously. It may be sensitive to water damage, the highest category of insurance loss in the residential environment. There is an architectural desire to use it without protective covering, and building regulations seem to have historically done a pretty poor job of tackling the risks associated with timber use in low-rise buildings. So we're in a situation where there is a perceived lack of pedigree as a building technique, yet great impetus to deploy it in the most complex types of buildings we have. Insurance cannot be a catch-all for reckless technical endeavour, so there's clearly some work to do to improve understanding. The use of timber is currently restricted to small building projects, but the ambitions for the future are looking to compete with the largest and tallest buildings we know. Barriers that limit timber use are generally enshrined in a country's building regulations, but these can vary greatly, and perhaps the exploitation of wood will occur better in countries whose regulations, unlike the UK's, have a business and property protection component attached to them, unlike the UK that focuses exclusively on life safety only. Crudely put, building in timber can be split into two key categories of light and heavy timber framing, with heavy timber framing split into the sub-methods of glue-laminated wood, laminated veneered lumber, and cross-laminated timber. Light timber framing is characterised by the use of thin stick wood and composite I-beams to create a structure that attains rigidity once the wall coverings, such as plasterboard, are fixed into place. The time of construction is known to be a period of heightened risk, since the fire-resisting skin is the last feature to be installed onto the building. However, even completed, these buildings have responded to poorly to fire from a property protection viewpoint. Whilst everyone was evacuated from these instances safely, the losses were total, a level of destruction that we are less familiar with these days. So these buildings might be no less safe, but challenges are known around build quality and accuracy, and it raises issues about whether occupancy should be related to the construction method used. Heavy or massive timber are structurally engineered products formed from the lamination of wood using glues to create members that have a greater strength for its size than a lumber beam of the same proportions. Laminating also offsets imperfections such as cracks and knot holes to create a more uniform building product. Glue-laminated, or GLULAM for short, comprises typically 7 layers of block wood or planks glued together. The resulting beams are used with a laminate in the horizontal plane. Laminated veneer lumber is similar to GLULAM, but the wood slices are only a few millimetres thick, more numerous, and the resulting beams are used with a laminate in the vertical orientation. As the name suggests, cross-laminated timber uses plank wood layers arranged alternately at 90 degrees to each other, forming very large construction panels. GLULAM and LVL are used in post and beam type construction, typically using metal brackets, and may additionally be post-tensioned to increase strength and span. CLT is used for panelised construction methods, where the walls themselves are structural. To overcome issues with fire protection of floors, composites of timber and concrete are sometimes also used. Here shows an example of post and beam construction with metal fixings at joints. Post-tensioning of beams with steel cables can increase load-bearing capability and span. This slide shows an example of panelised construction with cross-laminated timber building components. And here is shown an example of timber and concrete floor composite. The fire response challenges of high-rise buildings using these methods are many. Obviously wood burns, and there is a great tendency to overplay the role that charring plays in the protection of the structure. Whilst charring can delay failure, the fire is not extinguished, and most tests end with a hose being used. 40 stories up, or in a hidden void, we need to consider what takes the place of the hose in reality. Quality issues must also be considered all the way through from manufacture to installation to end use, including the accuracy of the structural models used for each timber type and glue combination when in use and involved in fire. Some work has shown that GLULAM beams can continue to lose strength after fire is extinguished due to heat-soaked lag, which could have grave ramifications for the responding services. Currently, most designs still use a plasterboard covering to ensure fire containment, but the architectural vision is certainly to be able to show off wood in all its beauty, and this raises challenges as it blurs the risks from structure and room contents. For the insurer, there are additional concerns around the extent of damage and repairability, particularly where destroyed aesthetics may require the replacement of otherwise sound structural components. Water damage is the highest category of loss in the domestic and residential environment and is obviously particularly prevalent in high-rise buildings. There are many opportunities for water exposure both during construction and thereafter, and these may have far-reaching implications throughout the entire lifespan of the building, if not carefully controlled. The impact of these may cause loss of strength through delamination, swelling or warping of the main structures, mould, discoloration and loss of finish, and rot. Buildings can have long lifespans, and the integrity of innovative building components to maintain their function correctly with time must also be considered. So in summary, these are new building methods and little is known of how they perform over time. Post-Grenfell, the encouragement of combustible materials in construction seems counterintuitive. Experience with light timber framing suggests our regulations are ill-equipped to support further combustible construction methods, particularly complex high-rise buildings. Insurers will inevitably be cautious. These are complex buildings, and insurance, as we've said before, is not a catch-all for reckless technical endeavour, even if done in the good name of sustainability. Management of fires in this environment might also be problematic for fixed systems and responding services alike, due to the presence of combustible voids and the potential for great consequential damage to be done during the process. The FPA, through Risk Authority, is currently working on a series of projects to ensure that insurers have the right information to hand to enable them to make their own judgment on insurability and risk control measures of this new breed of buildings. Thank you very much for listening.
Welcome back to the FPA Virtual Lab Day. The first person we have this afternoon for you is Dale Kindersley, our technical consultant. Dale's going to talk to you about residential water mist systems.
Good afternoon, ladies and gentlemen. My name's Dale Kindersley. I'm the Principal Consultant for the FPA. I'm convener of the Risk Authority Sprinkler Rules Working Group. I'm also co-convener of the Suppression and Detection Working Group with Dr. Jim Glockling. And presentation this afternoon with the slides is going to be on water mist, rules and regulations, service and maintenance, and applications.
This afternoon's presentation is just a run through on water mist, what it is, how it works, standards, applications, considerations, strengths and weaknesses, concerns in the future, FPA Risk Authority questionnaires, and service and maintenance. So what is water mist? It's a mist system, very similar to a sprinkler system. However, it uses finely divided water droplets in a mist of usually 200 microns. Droplets are created at higher pressures than traditional sprinklers through small orifices. And if I can offer a comparison, 200 microns for mist, 4 millimeters droplet sizes for sprinkler heads. It's generally described as a two-part action, providing thermodynamic cooling during evaporation, oxygen reduction through the steam displacement. It can be operated as a bulb system for general protection, very similar to sprinklers, and it can also be operated as a deluge system for compartment or local applications. So how does it work? Water mist works by rapidly converting energy to steam. It starves the fire of the oxygen it needs to burn. And what it does is the small water droplets allow the water mist to control or suppress the fire. It cools both the flame and the surrounding gases by evaporation, and it displaces oxygen around the fire by evaporation. Going on to standards, there are currently two standards available in the UK. There is the commercial and industrial standard, which is BS 8489 2016. It's a code of practice for the design and installation of water mist standards. But previously in the UK, what we used to use many years ago was NFPA 750. Obviously now we have our 8489 standard for commercial and industrial systems, and for residential and domestic we currently have BS 8458 to cover those disciplines. So where is water mist most applicable? So typical applications: gas turbines, fuel storage areas, restaurant commercial catering areas. Prisons have been used for water mist systems, chemical stores and life safety systems. But most recently, it's now been included in houses of multiple occupation, offices, schools, hotel and guest houses, restaurants and leisure facilities and health clubs. So when we talk about local application water mist system, we're looking at doing 3D or application to an object. Classed as an independent system, it provides complete deluge over the object. It discharges on the activation of a fire detection system, And as you can see from the diagram there, no pumps or water tanks required. You can do this from a cylinder system. Whereas when we're looking at general mist protection for total flooding and general protection, which is very similar to sprinklers, we're looking at pump systems, control panels, discharge nozzles, and we're looking at it can be used as an open deluge system, but most commonly, and very similar to a sprinkler system, a sealed bulb system. So considerations with regards to Watermist. It's a bespoke solution which requires performance testing to demonstrate its capability for specific applications and situations, which means that there must be a test protocol for the application that you wish to apply Watermist, which is unlike sprinklers. Installation standards are pretty much manufacturer specific for approved applications, and Watermist components are bespoke to the manufacturer. So if you have a system from one manufacturer and you wish to modify your system, you must use that manufacturer's components rather than another manufacturer's, as they're not interchangeable. Applications for Watermist generally suit life safety. They may not be suitable for property protection. It may be acceptable based on proven realistic fire tests for the specific risks as mentioned earlier. Each Watermist system must be proven for the fire scenario that it's going in to protect. Not all areas of a building can be protected from one manufacturer of a Watermist system, depending on their fire testing that they've done, and not all Watermist systems are equal. So what are the strengths and weaknesses? Strengths: very effective fire suppression in enclosed environments. They provide excellent environmental cooling properties. They can be a standalone local application system, as we've seen in one of the previous slides. Design and installation is based on fire test scenarios, so if you're applying a Watermist system to a certain particular area, you know that having done the research, it should be applicable for that particular scenario. It has reduced water supplies in terms of comparison to sprinklers. It has gas cooling properties, it's good on liquid fuel fires, and it's very good on high heat output fires. The weaknesses of it: it's not very good in ventilated spaces. It's limited to a ceiling height of 5 meters. It's not very effective on small fires. And unfortunately, within the guidelines, there's no design solutions for common issues in commercial premises, where we've got ductwork and cable tray issues, deep beams and bay construction, open areas between floors. Design considerations do not take these into account in the standards. There is no third-party approval scheme for designers or components. There's very little benefit once the water is exhausted, and it's not very effective on deep-seated Class A fuel fires. So Watermist, it's a quick summary. All suppression systems should be tested to meet 4 requirements. These requirements: it should meet the ambition of the system, and it should be well understood. Is it a life safety system that Watermist is being applied to? Is it item protection? Is it property protection? Is there an amount of business resilience required from the system? And therefore, the system should be capable of meeting these ambitions. The system should be designed in accordance with an appropriate national or international standard, which we have, BS 8489 and BS 8458. The system components should have been tested and listed in accordance with an appropriate standard. And the designer and installer should be in possession of third-party certification for any work that's designed and undertaken. So what are the concerns? Unlike sprinkler systems, Watermist systems are project specific, and each particular hazard or occupancy requires its own very specific design. Therefore, it's not possible to design a mist system by reference to one of the standards available. Unlike sprinkler systems, where we have BSEN 12845 commercial and industrial systems, or 9251 for residential and domestic, which enables a full design to be produced to a fully compliant system, this is not the case with the current Watermist standards. There is insufficient guidance, training and manuals available at this moment in time. Inappropriate referencing of sprinkler equivalency and assumed levels of reliability. This is unfortunately a reference that's constantly made for sprinklers and Watermist, and they are not equivalent in terms of what they offer. They have very short water supply durations, and the question is it appropriate for property protection? So what's the future? It's a promising technology. It makes it effective for some fire protection scenarios. It has supporting standards and certification schemes. They're just emerging, and there is a new suite of European standards, EN 14972, that are currently being written. Some are currently available through BSI, and some are still currently being worked on. The current British standards, they will be replaced by the European standards once they've been approved. More fire testing is being undertaken for approval of components, and manufacturers are developing new products to cater for different fire scenarios. So it's an evolving technology. Watermist questionnaires, as you can see on the screen there, this is something that's available through Risk Authority and the Fire Protection Association. And the Watermist questionnaires aim to understand the ambitions of each Watermist system. So as it's a complex kind of system and there's fewer standards to rely on, basically what the questionnaire is asking for is that all design elements have been considered, they use risk control logic and that has been followed, they're properly recorded, and they are owned. It's the only approach. The questionnaires ask details of the steps that must be taken for the provision of an effective Watermist response, and the questionnaires are split into 3 for different types of Watermist systems that are currently offered out in the marketplace. And any difficulty by any provider to complete the questionnaires should serve as a warning that the system is not appropriate for the risk that you're considering. Moving on to maintenance. Maintenance is covered in 8458 and it's covered in clause 7 and clause 8. Basically, we're looking at Watermist having a visual inspection of the nozzles and any hazard changes of use to the area that the Watermist system is applied to, or any system modifications or compartment modifications and changes. There's manual testing requirements, so a flow test of the system, an alarm test if there's any remote monitoring, and exercising of the valves that are on the system. And then a reinstatement of the system on completion of all the tests. However, there is a requirement that all service and maintenance activities are logged within a dedicated system logbook, and every service and maintenance is undertaken by a competent person. Watermist for commercial, slightly different. It's far more comprehensive. It's covered in clause 11 of BS 8489, and it's including, I haven't listed them all, but not limited to, weekly testing of the pumps, gauge reading and water levels, monthly testing of the batteries and the detection system, a quarterly test every 13 weeks. You must do a hazard review, check the nozzles, the pipes and the supports, the supply valves and the alarms. 6 monthly, dry valves, open nozzles, fire and rescue, valves, alarms, receiving centres and detection systems. On an annual basis, pump sets, storage tanks and strainers need to be checked, and 3 yearly the tanks and stop non-return valves. And as highlighted in there, there is a requirement to test the nozzles every 3 years for every commercial Watermist system. 10 yearly tanks and pressure vessels. So moving on to the Watermist nozzle testing frequency, as required under the standards, a selection or a percentage of the nozzles installed shall be tested. So as I alluded to on the screen there, under the British standards for commercial and industrial, Watermist nozzles must be tested every 3 years. Under NFPA standards, every 5 years for a bulbed or automatic system, and if you have open nozzles for a local application system or a deluge system, it's every 10 years. Under the American standard FM Global, it's every 5 years. The new European set of suite documents 14972 will be every 5 years, and offshore will be every year. So with regards to testing, just to let you know that the FPA offer a Watermist testing facility, competitively priced, and we produce a detailed report 12259-1. Details are available on the email shown on the screen, sprinklers@thefpa.co.uk. For more detailed information on Watermist, Dr. James Glockling, the Technical Director of the FPA and Risk Authority, has recently undertaken a Watermist webinar and called Watermist Why It's Complicated, and this is available as a free download on the Risk Authority website shown on the screen. Thank you very much for your time and enjoy the rest of your day.
Thanks Dale, that was really good. Next we're going to show you around our sprinkler pump facilities, and your host for this will be Ian Walters, our Principal Consultant. So this is our purpose-built installation control valve chamber, and in here we've got a selection of installation control valves of different types. We've actually got 14 valves in here so that delegates who come on our courses can get a good hands-on experience of using the valves themselves. This is purpose-built, as I said, and last year we had over 130 delegates attend our courses to do hands-on training in this very room. So I'll just walk around and show you the different types of valves that we've got. Starting at the end here, we've got deluge valves, dry and wet valves, and we've got a dry pipe valve here, a wet installation control valve, which is obviously the most common valve that anybody uses, and then we've got other deluge valves trimmed in different ways to be pre-action valves. We've got pre-action valve, double acting, and we've got a butterfly wafer alarm valve here, the old type. So it's a lot of those sold, so obviously if you want to get experience of using that one, that might be the thing to use. We've got more wet valves, and then as we look along here, we've got alternate wet and dry valves. At the back there we've got a project fire zone control valve, and then on the corner there we've got a pre-action valve which has got a detection system. Behind there with the light on you can see an electronic panel which is lit up, and it's got a simulation to a detection system so that we can enact a sort of real life experience of a detection system going off and setting off the pre-action valve. On the table here we've got a lot of examples of pressure switches and flow switches and valves that we've taken out and stripped down so that you can get hands-on experience of actually taking these things apart and just having a play around with it really, but you'll learn a lot from the experience of being in this room. This is our sprinkler pump room, and we've got 3 pumps in here. We've got a diesel pump, an electric pump and a small jockey pump. Obviously the pump room is an essential part of the kit for a sprinkler system, and delegates coming on our courses will get hands-on experience of using this equipment. I'll walk you through the pump room now and I'll show you the testing equipment that the delegates can use. So in the background we've got what would normally be a duty pump, which is the electric pump. It's an ordinary has a Group 1 pump with the electric supply and electric panel behind it, all of which will be explained to anybody who comes on the course. On the right here we've got the diesel pump, which is normally a standby pump. This is actually a high hazard pump. The 2 pumps don't match, but that gives delegates a bit more sort of real world experience than just coming on a course, because ideally the 2 would match, but obviously you're going to learn a lot more from having 2 mismatched pumps. And in the back there we've got a small jockey pump as well, which obviously tops up the system pressure. It's all connected into the pump start board, so we will be showing you how to use this pump start board. Obviously we've got the pressure switches for the 3 pumps, starting with the jockey, the electric and the diesel pump, and we'll show you how to test that, how to bring the pumps in, and then more importantly we'll be showing you how to do a pressure and flow test for each pump, so we can do a pump performance test using the flow meters. We've got a flow meter here and the flow test line which turns the water back into the tank located just outside. Our water tank is just through the wall there, and it's a fully approved LPCB water storage tank. So just running around the room, obviously we'll show you which valves to operate and which ones need to be closed, explain the pump starter panels such as this panel, and towards the back here we've got the remote alarm panel with all the signals on it. We'll explain what signals you should be receiving and the function of this panel, and generally talking you through the LPC rules at the same time to make sure everything's fully compliant with the current standards. Okay, so this is our sprinkler tank. It's a purpose-built LPCB approved sprinkler tank. It's of 19 cubic metres, so it's slightly smaller than a normal sprinkler tank, but we've had it built so that you can see all the ancillary fittings and get experience of it. It doesn't just apply if you're a installer or a maintainer, but if you're a designer, by having this here you can see what you actually need to put on the tank and the amount of space that it takes up. Our particular tank is a modern tank. It's got the manway at the base so that you can get in and out of the tank if you need to go and service the tank. Obviously we've got the contents gauge and the nameplate here which tells you the capacity, the diameter and everything else. But the tank itself is fed from the water supply there which rises up the tank, which is this pipe here has got trace heating lagging on it to stop it freezing. There's an immersion heater there to stop the ball valves from freezing, and then the ball valve housing on the top there is accessible by a ladder. We've got the ladder which is currently in the pump house. We can bring that out and put it against the tank, fit it into the frame, and you can go up on top of the tank, have a look into the tank, work the ball valves and see for yourself, so it's good experience. Over here we've got the drain, so we can drain the tank, which is also lagged to prevent it from freezing. And then on the top here you can see the telltale and the overflow pipe, just in case there's a problem. So what you've got here is a fully functioning sprinkler tank for you to come and look at and get familiar with. This is our sprinkler head testing facility. It's purpose built by the FPA. We're here 24 hours a day testing. It's a constant process, and we test a lot of heads every day in batches. If you've got a sprinkler system and you want to send heads here for testing, it's quite an easy procedure. This is a sprinkler box. We send you the box. If you get your sprinkler contractor, your maintenance contractor, to take the sprinklers out on a sample and put them into these boxes, you can send them back to us here at the FPA. What you do is put it into the box there, use the prepaid label that comes with the box, put that on, take it to your post office, and it'll come back to here at our test facility. When it gets here, it'll be logged in by our trained staff. So, as I say, it's a constant process. The requirement for this is in BS EN 12845, commonly known as the 25-year head testing. 25 years is really the maximum period. Manufacturers may insist that you get it done, or recommend that you get it done sooner, but things like MJCs and dry pendant drops could be tested every 5 years. We can test all of these things for you, so we've got the facilities here to do it. We've got the temperature testing bath on to the right here, and then we've got the actual flame tests behind. And we've also got the facility to do a K-factor test on the sprinkler, and also a pressure test, so that if the head fails for any reason, we can subject it to increased pressure up to about 6 bars to make it work. So we really can test every kind of sprinkler that you've got. Thanks Ian for showing us all about sprinkler heads. Next up, we're going to use our variable height ceiling to show you the effectiveness of sprinkler systems. This is going to be done by George Edwards, Head of SPG Trials.
Okay, so this is our variable height ceiling, which we've got down at our test facility in Blockley. We can raise and lower the height to anything up to 6 metres, and we use it for a number of tests. It's currently set at 3.5 metres for this sprinkler demonstration that we're about to show you. So we've got 4 identical sprinklers at different ceiling heights, and this is going to show how they have different response times with different ceiling heights. So all 4 sprinklers are positioned in accordance with the LPC sprinkler rules. We've got one 75mm from the ceiling, one's 150mm from the ceiling, one's 225mm from the ceiling, and the last one's 300mm from the ceiling. Now the LPC rules do recommend that you position them between 75mm and 150mm, which is the first 2 heads that I mentioned, but all 4 heads are compliant. So the test itself, we've got a gas burner which we've set up, so it's a propane gas burner which we've set up with our mass flow controller, and that allows us just to regulate the gas flow so we've got a consistent fuel load, and we will set it off and then look at the response times for the sprinkler heads. Okay, so we've got our pilot flame on top of the gas burner, and you can see now how the gas has gone through and the gas burner is properly lit and the flames are starting to lick the ceiling. That's the first head to go off, is the 75mm head. Next is the 225mm head to go off. The 300mm head actually goes off before the 225mm head, and lastly we've got the 225mm head going off, which concludes the test. Okay, so that concludes the test, and we can see how there was quite a difference in response times between the 75mm head and the 300mm head. The heads sort of mostly went off in order, except for the 225 and 300. It just sort of shows how sprinklers going off can be a little bit inconsistent and how fires are inconsistent. But hopefully that demonstrates how the ceiling height is quite important, and just because they're all compliant with the sprinkler rules doesn't mean that there isn't more that you can do to make sure that your system activates as well as it possibly can. And we've sort of shown off our facility itself with the variable height ceiling. This is something that we've used for many different clients, and we've used it for sprinkler clients before. For example, we worked with a company called Innertech from Hong Kong, and we set the variable height ceiling to the height of their warehouse facility, installed racking from their warehouse facility, and tested their sprinkler system on site with a variety of different hazards to demonstrate how effective it was for them, and looked at different additives like foams and things.
Thanks, George. Now we have something really exciting. We are showing a reconstruction of a car park fire that was done for the One Show. George, over to you again.
Okay, so the One Show came to us because they wanted to recreate a video of a fire that happened in the Liverpool waterfront multi-storey car park back in December 2017. So we obviously didn't want to set fire to a whole car park to recreate it, so we had to do it in lots of small stages, which presented a few challenges to us. So to start with, we had a shot of sort of fuel burning through a fuel tank in a vehicle, simulating what happened on site, where fuel burnt through one vehicle, the flowing fuel spread to other vehicles, which then spread to a gutter system where it melted through, fell to the floor below, and then carried on burning to set fire to extra cars on the floor below. So one of the big challenges we had was creating a flowing fuel fire that went in the direction we wanted it to in a safe manner without burning people or cameras. So the way we did that is we had a large container filled with burning diesel. We slowly pumped water into the container, which allowed the diesel to rise up because it floats on top of the water. And once the diesel reached the top of the container, it came out through a lip that we'd created that had enough momentum to carry it along towards where we wanted it to go. So to start with, we had it flowing off towards a gutter system. We had to be careful about using guides and things on the floor because we didn't want them to appear and obscure too much of it from the camera's point of view. And that was the end of that shot. We then had to film it from below. So we made a false ceiling with a plastic gutter system, and filmed that from below. And so you could see the fire melting through the gutter system and falling to the floor below. And then from there, we had a separate shot of the fuel flowing towards the car, and it set fire to two 4x4s inside a fake garage that we had. So we start with a shot of the fuel flowing out of our fuel flowing system. So you can see it coming out of the spout here, which is sort of just below the, which runs down from the top of the system. And the fuel's sort of semi-lit inside the pipe, but as it comes out, it comes out lit and stays lit with the rest of the flowing fuel. And you can see our guides here either side of it as we guide it along into the gutter system, and it's just sort of slowly crawling its way along. So here you can see it flowing into the gutter system, and you can see the flames looking out in different places. It's quite a smoky fire because we use diesel for these, because our sort of research told us that most of the cars in the car park were diesel-based cars. And you can see the flames looking up quite ferociously through parts of the gutter system. As this is happening, so we filmed this in a concrete gutter system, but on site there was actually a plastic gutter system or aluminium in places, and these melted through from the intense heat here. And that's how it got from one floor to the floor below. And you can see here a nice close-up of the flames licking through the gutter. So we now move to a shot below the gutter system. So we've got our false ceiling here with a plastic gutter system, and the diesel sort of burning its way through. You can see how it quite quickly gets through the gutter system, and the gutter system starts to bow and buckle underneath it. One of the challenges that was presented by this fire was the large sort of curtains of flame falling through the floor, which made it very difficult for firefighters to put out the fire on site. And it also created the phenomenon of the fire spreading downwards at the same speed that it was travelling upwards. Normally it's quite difficult for fires to spread down below floor. And so you can see the gutter system here starting to buckle, and once it completely goes there'll be quite a lot of fuel falling through. As you can see now, we've got that sort of curtain of flame effect trapping down from the ceiling. So we now move to a shot of, this is quite late on in the shot, of the fuel flowing along the floor underneath the car. So we used 4x4s because again these are quite representative of the cars used on site at the time. And you can see how the fuel sort of flowed along underneath the car, and it's now starting to light car number 1. Next to it we had a second car, just to show how the fire could spread from one car to the next. You can see lots of black smoke here, some of it coming from the diesel and some of it coming from the plastic in the car as it starts to melt through the floor. And as we move to a wider shot, you can see how the flames are licking up in between the two cars as the fuel spread from car number 1 and almost all the way to car number 2 now. And pan out to a wider shot as well. So as the compartment gets more smoky, you'll see our infrared shot here. Again, showing how the fire is sort of mostly underneath car number 1 and in between car number 1 and car number 2. You can see how the fire is licking through the back window, but you can tell from the black windows at the front that it's not got through them, and because the infrared light can't get through the windows, that's why they're so black. As we move back to the normal camera, you can see how smoky it is in the compartment from the diesel and the plastic fumes. Again, another one of the challenges on site and in a car park like this is how quickly it smokes out and how difficult it gets for vision. You can see how the infrared camera is still seeing everything clearly. And moving towards this sort of end of the test here, once the cars have actually burnt out quite a bit. And we actually manually extinguished our cars on site after about 15 minutes of burning. So we had firefighters on site ready to put them out. We also had a suppression system inside the cars. We just had a sprinkler system hidden inside the cars to help put them out at the end of the test. But you can see how it still takes quite a while. This is another 20 minutes on from earlier. And they're still pouring water in the car because there's lots of compartments to them, and yeah, they are quite difficult to put out. And you can see how parts of the car are still reigniting, even sort of 30-40 minutes after the test is finished. So the crew's still on hand to make sure everything's gone out, but just sort of shows the challenges of these sorts of fires. So this was just one example of how we can create different fire scenarios to build up a picture of a larger fire by breaking it down into lots of smaller fires. This was just for demonstration purpose for our client, but we can involve instrumentation, heat flux sensors, thermocouples and things like that to help answer any sort of questions or problems that you might have. And yeah, no fire is really too big or too small for us. We can take on any challenge and design any test to meet your needs.
Thanks George. Now go and have a rest. Next we have another case study for you, which we carried out for a customer of ours called Plumist. This is a Watermist system. To talk you through this will be John Hardbottle, our Senior Trials Manager.
So next up we're going to show you a video of a Watermist test we conducted for Plumist earlier in the year. Plumist came to us, they wanted to conduct a series of tests to examine how their system interacted with a number of realistic scenarios within a controlled environment. This was in order to gain a better understanding of their system and knowledge of how it can be, where improvements can be made. So here we see a video we conducted for Plumist. We constructed a 10 by 5 by 2.5 metre plasterboard room and installed this suppression system in the room. The fuel load for this test is a front room fire test comprising of a 2-seater sofa, a upholstered chair, one side table and one coffee table, and then the fire is lit in a waste paper basket on the right hand edge of the 2-seater sofa. You've just seen one of our FPA staff come in and light the fire. The fire gradually develops and smoke is produced. As the compartment gets smokier, the system begins to react. Here we can see the fire is now spread from the waste paper basket to the arm of the 2-seater sofa, starting to grow. The fire's not yet spread to the upholstered chair, but the two-seater sofa is more involved. We just changed over to a thermal imaging view. The red area is the hot spots in the room. The blue and green area are the cooler regions. You can see the fire plume there is almost reaching ceiling height, and we're starting to get a hot spot on the ceiling. For these tests, we had a number of thermocouples located at different heights in the room and above the fire, and we had video cameras recording the fire's development. It's to give us an idea of temperatures at remote areas in the room. Now the fire's grown to a suitable size that the Watermist system is activated. It's spraying a jet of high pressure water mist from the left hand wall directly towards the fire. Temperatures in the room are rapidly cooled. The seat of the fire is still producing heat, but the rest of the room from the thermal imaging we can see is relatively cool. The system itself, when it interacts with the fire, produces a large amount of water vapour, so the CCTV is now showing a whiteout of the room, but from the thermal imaging we can still see how the fire is developing. Only after a couple of minutes the fire is heavily knocked back and suppressed. There, only after a couple of minutes the fire is heavily knocked back and controlled, although still continuing to burn on the arm of the chair. But the rest of the room is cool. We ran this test for 30 minutes after activation of the suppression system. The video speeds up a bit here now to take us forward to the end of the test. The fire continues to burn in and around the chair, but is under control and has stopped spreading from its point of origin. Now we just see a few small hot spots in and around the arm of the two-seater sofa. The waste paper bin has been fully extinguished. As the test continues, the hot spots continue to fade. And the room and the temperatures around the room are back down to cool levels. We see the fire is very much dwindling now, a few hot spots, but under control and on the way to be extinguished. Post-test, the system was shut down and the smoke and water mist allowed to clear from the room. Here are a few example photographs of the fuel load. Here we can see the arm of the two-seater sofa was heavily burnt but did not spread from the left-hand side. We see on the right there the upholstered chair, very minimal damage, and the side table has some charring, but fire has not spread to it. And the coffee table in front of the chair is undamaged. From another angle, the vast majority of the two-seater sofa is intact. Although it did ignite, it hasn't spread from the left-hand side. Following the tests, the client received all the data and video footage recorded during the test for their analysis and recommendations from the FPA. Panelised are now looking to conduct further testing with the FPA in order to further develop their system.
Thanks, John. For our last talk of the day, we have Benny Rooney from the Scottish Parliament. Benny is going to be talking about standards testing. Over to you, Benny.
Good afternoon. My name is Veneered and I'm the Senior Policy Officer of Technical Author of Section 2.5 and Building Standards Division of the Scottish Government Directorate for Local Government and Communities, normally based at Livingston, but like most others I'm currently working from home. And prior to taking up my current position just over a year ago, I worked for the Scottish Fire and Rescue Service for the previous 31 years, where I spent time with the Scottish Fire and Rescue Service between operations and fire safety enforcement functions. Today I'm going to give you a fairly brief overview of the role of standards testing as well as British and European standards within the Scottish Building Standards System. I'm going to concentrate on how they assist in the delivery of guidance within Section 2 Fire, but the same general principles apply to other sections of the technical handbooks. I'll start by giving a very brief overview of the Scottish Building Standards System before moving on to the more specific examples of how British and European harmonised standards assist in ensuring buildings are fit for purpose. In case anyone might be wondering why this is important, let's not forget the next two images. I think we should remember one of the main reasons bringing us together today, and without wishing to preempt anything coming out of the Grenfell inquiry. However, I don't think it's any great secret that the cladding system did not achieve an A1 or A2 classification under Eurocodes, nor had it been tested under BS 8414. And here in Scotland, we've had our own issues. Fortunately, the collapse of the outer reef of masonry of Oxgang Primary, which was due to inadequate tying of the two reefs, occurred out with school hours, just 1 hour before the children arrived for the day. Otherwise, there could have been many children and their staff seriously or even fatally injured. Essentially, the wall construction did not comply with Eurocode 6, Design of Masonry Structures of PD 6697/2010 in relation to wall tie length, embedment, etc. So to provide some background, building regulations are legal instruments intended to ensure that buildings, when constructed and used in accordance with the regulations, provide socially acceptable performance with respect to the building and the welfare of its occupants and the community in which the building is located. This is often accomplished through regulatory controls on the design, construction and operation of buildings, covering such diverse areas as structural stability, fire safety, heating, lighting, ventilation, plumbing and sanitary facilities, and may include accessibility, affordability, indoor air quality, energy and sustainability. The Building Scotland Act 2003 is the primary piece of legislation that allows everything within the building standard system to be implemented. The Act allows Scottish ministers to make the building regulations and the building standards which come into force under Regulation 9. It also allows them to issue guidance in support of the building regulation. The Act also allows ministers to appoint verifiers, which are currently referred to local authorities, and approve certification schemes such as SER's Certification of Design Scheme for Structural Designs as part of both verification and certification appointments. The Building Standards Division carry out audits as part of the appointment criteria. So we have 17 building regulations within Scotland, with Regulation 9 bringing in 72 mandatory building standards. The only way to comply with Scottish building regulations is to comply with any and all applicable building standards. To assist in compliance with the building standards, Scottish ministers have issued 2 technical handbooks, one for domestic buildings and one for non-domestic buildings. The guidance does not need to be followed, but the Act states that evidence of meeting the guidance may be relied on in any civil or criminal proceedings as tending to negative liability for an alleged contravention of building regulations. The guidance in the technical handbooks refers to a variety of other guidance documents, including British and European standards throughout. We routinely carry out technical reviews in various aspects of the technical handbooks, the latest considering immediate outcomes from the Grenfell tragedy, but it's acknowledged that this is an area that we will probably have to revisit once all the recommendations from the Grenfell inquiry are published. In the aftermath of the Grenfell Tower fire in London, the Building Standards Division of the Scottish Government undertook a review of certain aspects of the building standards fire safety in Scotland. Meacham Associates conducted research on regulatory appropriateness of cited reaction to fire testing technical handbook Section 2 Fire Standards 2.4 to 2.7 on behalf of the Scottish Government. The objective of this project was to conduct research and provide an independent opinion on the regulatory appropriateness within the Scottish building standards system on the suitability of the British standards and harmonised European standards for reaction to fire testing as cited in the annexes of the Technical Handbook section to fire for building standards 2.4 to 2.7 and whether either or both should remain. In conducting the research, several factors were considered, including issues associated with risk levels, applicability of the same test method for different purposes, for example, interior lining versus external wall systems, alternative test methods, and verification of designs using cited or alternative test methods. The focus of this research was directed to be on the regulatory use of standardised reaction to fire test methods within building regulations in general, and within Scotland in particular, and not on specific scientific or technical merit of specific reaction to fire test methods considered. It was deemed important to understand the role of standardised fire test methods, in particular reaction to fire test methods, in assessing the fire safety performance of building materials, systems and components for buildings in Scotland for regulatory compliance with the standards. In this report, a standardised fire test method was defined as a description of a methodology, apparatus and associated test parameters that are used for assessing one or more attributes of fire performance of a material, component, system or assembly for the purpose of defining a common benchmark or benchmarks for performance, which can be uniformly applied to a wide range of products using equivalently designed and functioning apparatus by different people in different laboratories or facilities with a tolerable level of variability. Now, as we know, fire is a very complex phenomenon, which is influenced by the characteristics of the fuel, for example, ignitability, combustibility, flame spread potential, the source of ignition, example again, the temperature, energy, distance to source, duration, the configuration of the fuel, any confining barriers such as the floor, walls and ceiling, compartment fire, and ventilation conditions. As such, it is very difficult to develop test methods that accurately reflect the full range of material, component, system or assembly behaviours across the broad range of potential ignition and fire scenarios. With respect to materials controlled or considered within building regulations, there are two basic types of standardised fire tests: fire resistance test and reaction to fire tests. The general intent of a standardised fire test method is to provide a level of confidence that all products assessed using the standardised method will be tested in the same manner, evaluated using the same criteria and certified as performing in a similar manner under the specific parameters of the test. In developing standardised fire test methods, the general aim is to produce an approach that can deliver outcomes that are A, consistent from test to test for specific material or product regardless of location of the test facility, and B, do not unduly disadvantage any particular material, component, system or assembly with respect to broadly agreed measures of performance. The measures of performance developed for a specific standardised fire test method will vary by the type and nature of the test parameters, based largely on physical and chemical properties of fire, for example, ignitability, flame spread potential, smoke production, volume and or rate and mechanical stability, etc., etc. The measures of performance are typically linked in some way to a representation of tolerable levels of hazard, risk or safety in use, which is generally defined within regulation, for example, the building standards. Fire resistance tests are largely focused on two primary areas: evaluating the ability of passive building elements, for example, fire barriers and openings therein, to contain, restrict or control the spread of fire, and evaluating the mechanic resistance to fire of structural elements, for example, columns, beams, floor slabs, etc. Whilst reaction to fire tests are used to evaluate fire properties, performance of materials, types of fire properties that are assessed include ignitability, combustibility, ease of extinction, flame spread, smoke release, weight and mass, heat release and toxic gas releases, and toxicity and concentration. Reaction to fire tests may evaluate one or more fire properties. In general, the more properties that are being assessed and the more complex the specimen, for example, a system or assembly as compared to a single homogeneous material, the more complex the test method will be, including apparatus and procedure. And often the larger the test will be as well. In general, the scale of the test is related to the hazards of concern, the scenarios in which the material, component, system or assembly is likely to be used, and the fire properties being assessed. Generically, the scales are small or bench, immediate or medium for assembly, and large or full or real scale. The appropriateness and scale of the test method relative assessing of the fire properties of a material, component, system or assembly is largely driven by the scenarios of concern. Depending on the scenario, a particular test may or may not be entirely valid on its own. Comprehensive in situ testing of full-size representation, for example building, is not economically or societally practical. Instead, the use of a range of standardised fire test methods which measure different fire performance attributes across different scales are generally proven to be a practical and cost-effective approach. As a result, there are hundreds of standardised fire tests which are used to evaluate fire properties of materials, components, systems or assemblies across a wide range of applications. Given the wide range of uses of many different given materials, components, systems or assemblies, there is a need for a wide range of standardised fire test methods at different scales to help provide confidence that the fire properties of the material will be adequately understood across applicable scenarios. Fundamentally, the regulatory purpose of standardised fire test methods is to provide a legally enforceable and broadly accepted pathway to demonstrating acceptable fire performance of the material, component, system or assembly with respect to fire and life safety objectives, and where applicable, protection of firefighters' property protection, sustainability and resiliency objectives of the building regulations. In the case of Scotland, this would include fire, life safety, fire service and sustainability. Regulation 8 of the Building Scotland Regulations 2004 applies to all building work and requires that materials, fittings and components used in the construction of buildings should be suitable for their purpose, correctly used or applied and sufficiently durable, taking account of normal maintenance practices. It also recognises the European Regulations 305-201-EU Construction Products Regulations CPR, which came into force on 1st July 2013, replacing the Construction Products Directive. This regulation requires that products covered by a harmonised European product standard of conforming to a European technical assessment should normally have a CE marking. There are over 300 British and European harmonised standards cited in the technical handbooks, and meeting the guidance within these can be used to evidence the suitability of materials and design or installation. According to the BSI website, there are currently 37,000 British standards, and we cite less than 1% in our technical handbooks. The building standard system is concerned with the health, safety, welfare and convenience of people in and around buildings. It's also intended to further the conservation of fuel and power and the achievement of sustainable construction. However, as far as building standards and fire are concerned, it's the health and safety and welfare of people in buildings that is of concern. We aren't really concerned with property protection, other than in schools where automatic fire suppression systems are required to try and stop disgruntled individuals burning down their local school. I should also point out that we do think firefighters in buildings as people, and so we have standards to cover their welfare as well. So to allow the occupants time to escape and to give firefighters time to tackle the fire, building standards expect fire spread to, from and within the building to be limited. You may be aware that in October last year we introduced changes to make building in Scotland even safer, and further measures will be introduced early next year with sprinklers required in all new social houses, all new flats and some new multi-occupancy homes. As we've heard today, there are many different types of British and European standards. The ones that relate to the requirements of Section 2 fire are those that set fire test methodology. As you'll see in the next few slides, the requirements for resistance to fire and reaction to fire are spread throughout the guidance. The building standards 2.1 to 2.7 relating to resistance to fire, reaction to fire and the vulnerability of roof coverings. The fire resistance of a material or product is the time taken for the fire to penetrate the material or product. It has to be accepted, however, that the fire test is an indication of the fire resistance, not a guarantee. There are many factors that will affect the resistance in the real world, not least of all which is the actual fire load. The guidance in the technical handbooks talks about fire resistance durations and sets 3 categories: short, medium and long, which Annex 2A in the domestic handbook or 2D in the non-domestic handbook clarify as 30 minutes, 60 minute and 120 minute period of fire resistance respectively. We cite both British and European standards as a means of determining the fire resistance of products or materials in Annex 2A and 2D. This is quite unusual, as when there's a European standard we would normally just refer to that alone. However, fire tests are not cheap things to have carried out, and we have limited testing facilities in the UK. So it was decided that it would not be reasonable to put manufacturers to this expense and potential obstruction when getting their products to market, and continue to make reference to British standards, whilst at the same time introducing European standards into the building standards system. Like all fire tests though, it is not a guarantee that the product or material will achieve the required outcome. As indicated, a standardised fire test method is not a test or measurement standard, in that it provides information on the acceptability, performance as in pass or fail, usually under some standard condition, e.g. Class A or 1 hour, or to provide data that can be used to determine acceptability or performance. Reaction to fire is considered on an element basis. That is to say, it is the way that part of the construction, for example, a separating wall or external wall cladding, reacts to fire. Basically, does it go on fire, and if it does, how quickly? As far as reaction to fire is concerned, we have 5 risk classifications. These are referred to in the technical handbook guidance as non-combustible, low risk, medium risk, high risk and very high risk. Annexes 2B and 2E of the current technical handbooks refer to both British and European standards as a means of evidencing the reaction to fire classification. Again, parts of the BS 476 suite of test standards are referred to, along with a variety of European and ISO standards. However, it has always been recognised that the British standards referred to weren't very well suited to this application, and in a recent review of the fire standards guidance, the decision was taken to remove the BS 476 suite of standards as a route to evidencing reaction to fire. So from the 1st of October 2009, the only means of evidencing that the product or element will achieve the required reaction to fire is via the European or ISO standards. Building standard 2.8 attempts to limit the spread of fire from one building to another as a result of burning embers, flames, or heat. So here we need a standard that can indicate the vulnerability of roof coverings, that is to say their ability to resist penetration from fire and limit fire spread. The guidance sets 3 criteria that should be met depending on the distance the building is from the boundary. The 3 criteria are low, medium and high vulnerability. Once again, we look at BS 476, this time part 3, which is a test and classification standard that measures the capability of a roof to resist penetration from fire and flame spread when the external surface is exposed to radiated heat and flames. We also reference BSEN 13501, Part 5, Double DEND 1187. The format is purely a classification standard for construction tested under 1187. I've already covered reaction to fire test methodology for reaction to fire, but felt it was useful in the current climate to raise it specifically in relation to external wall cladding. As I said earlier, we dropped the reference to BS 476 suite of standards as a means of evidencing adequacy of reaction to fire. We have, however, retained BS 8414 standards in conjunction with BR 135 as an alternative roof compliance, and this has caused a bit of discussion, as you will be aware. During the review, we looked at similar tests around the world and concluded that the 8414 test was certainly one of the most robust test methodologies, if not the most robust in the world. And indeed, the international members of the review panel agreed with this view. The fire in the test is representative of a 4,500 megajoules of energy over a 30-minute period with a peak release rate of 3.5 megawatts, equivalent to a post-flashover fire emanating from a window or door. Post-Grenfell, the BS 8414 methodology came into the great deal of criticism from various quarters, and BSI decided at an early juncture to carry out a review. This review has been completed and updated versions of BS 8414 were published earlier this year. At the request of the Westminster Government, BSI also drafted a new standard to cover extended field of application of BR 135 reports on the BS 8414 tests. The new standard number BS 9414 has also now been published. Scottish Government officials were committee members of both committees considering these standards and the 8414 standards, as well as the new 9414 standard, and are referenced in the technical handbook guidance. As I indicated at the beginning of my presentation, the technical handbook guidance does not need to be followed, and alternative means of compliance may be adopted. This is an approach that is used in respect of Section 2 fire more than any other section of the technical handbooks. We cite BS 7974 within the introduction to Section 2, but do not provide a commentary on its use. Other standards may also be used, for example, BS 9999, however, we do not cite this within the guidance, as it is very much based on approved document in England, and essentially referring to another country's standards, albeit indirectly, is not a good thing. Use of fire engineering does tend to be done on a piecemeal basis rather than taking a holistic approach to the solution. And whilst in some instances this is a reasonable, in many cases it is not and produces a bit of a disjointed design solution. So I've touched on a couple of aspects of the amended guidance which came into force in October in previous slides. The changes involved a slight change to Building Standard 2.4 to remove a perceived loophole around the unseen spread of fire at concealed spaces. We've taken unseen out and changed concealed spaces to cavities. We've introduced a requirement for at least 2 escape stairs in high-rise domestic buildings and an evacuation alert system for use by the Scottish Fire and Rescue Service. This was another item to come out of the fire safety review. It was felt that it would be beneficial to firefighters to be able to activate sounders within each flat, alerting the occupants of the need to escape if necessary. This may be a single floor, multiple floors, or on extremely rare occasions the whole building. There would be a single activation panel on the floor that the firefighters would normally be expected to enter the building by, and this would only be accessible by them. In support of this initiative, BSI agreed to develop a standard providing guidance on the expectations of such a system. And this standard, BS 8629, is currently published, and we extremely grateful to BSI for producing this new standard, and would like to publicly thank them for this. Again, as I said earlier, we are removing the references to BS 476 reaction to fire tests, as they are not really suitable for material intended for use on the outside of buildings. The Euro standards aren't perfect, as they use a relatively small fire load in the test, but it was felt that they are better than the British standards. Basically, we require A1 and A2 materials or a BS 8414 full-scale test with a BL 135 report on the test. These requirements apply to all buildings with a storey height of more than 11 metres above the ground, both domestic and non-domestic, all entertainment and assembly buildings, but there will be an exemption for small buildings, that is buildings with a floor area of less than around 500 metres squared. And all residential care buildings and hospitals are again with an exemption for small buildings, but this time around 200 metres squared of maximum floor area. You may be aware that the Futures Board programme was set up to provide guidance and direction on the development and implementation of the recommendations made by the review panels on compliance and enforcement and fire safety, which reported in 2018. The Futures Board remit is to strategically advise and direct a broad programme of work aimed at improving the performance, expertise, resilience and sustainability of the Scottish Building Standards framework and services across Scotland. The programme of his work has been split into 7 work streams: a new compliance approach of the compliance plan, verify a workforce for strategy and action plan, digital transformation, certification strategy, technical strategy, verification standards and delivery model. You'll also be aware that on the 20th of January 2020, the UK Government's independent expert panel published consolidated advice for building owners of multi-storey, multi-occupied residential buildings in England. On the 30th of March 2020, Scottish ministers agreed to set up a technical working group to develop a Scottish advice note to determine the fire risk posed by external wall systems in existing multi-storey residential buildings. The draft Scottish advice note is now out for consultation. To gain feedback, officials are engaging with key stakeholders and organisations, and there are public webinars there for anyone can join the discussion. Lastly, Building Standards 215 currently requires automatic fire suppression systems in residential care homes, hospitals, enclosed shopping centres, schools and high-rise domestic buildings. We're expanding the requirement for automatic fire suppression systems to all flats, regardless of height, and this will be introduced in 2021. The regulations to extend sprinklers to all new flats, maisonettes, new social housing and multi-occupancy residential building, referred to as HMOs in 2018 work, will be laid in Parliament, and amendments to the technical handbooks will follow in a few weeks' time. Lastly, many thanks for listening, and I hope you have found this presentation useful.
Thank you, Benny, and thanks to everyone who's participated today.